Sin square. Good. Now let's do an example with discrete time Fourier transforms. Discrete time Fourier transforms. And this will be actually useful. You will use it a lot in the homework. So similar to the similar when we did in the previous workshop, we did exponential minus alpha t ut, and we did the continuous time Fourier transform for this signal, and it was 1 divided 1 by alpha plus j omega. And this Fourier transform actually is very useful, very, very useful, because at the end, most of the time, let's say if you are doing, it's very useful when you're doing inverse Fourier transform. You will have some Fourier representation of a signal which is written in terms of omega, a function of omega divided by, let's say, alpha plus j omega or beta plus j omega. And then you should use the partial fraction expansion and rewrite this one in terms of, let's say, a divided by alpha plus j omega plus b divided by beta plus j omega. And then you find the values of a and b. And now you will have the same formula as this one. So you'll be able to easily do the inverse Fourier transform after writing the signal similar to this form. So this form, the inverse Fourier transform of this form is basically this one. This is actually ut. So the inverse Fourier transform of this one is this one. So you'll have exponential minus alpha t ut here scaled by some factor, and then the same thing scaled by another factor. That's why this one is very important to remember. And you will find it actually in basically all tables of Fourier transform pairs. For the discrete time Fourier transform, we have also equally important signal that we need to know, also its Fourier transform, which is xn equals some constant to the power of n un. And we're assuming that gamma is less than 1. And you will see why we need this assumption to make sure some geometric series will converge, basically. So this is the signal. We need to find discrete time Fourier transform x. X of exponential j omega. Now we'll use the analysis equation. Is a summation from minus infinity to plus infinity, n xn exponential minus j omega n. If we substitute this signal in here, we get n equals minus infinity to plus infinity gamma n un exponential minus j omega n. Now, because of this unit step function, which is in this n, un, and otherwise it's 0. So the summation will become from 0 to infinity. Here's because because when n is less than 0, we are multiplying with 0 and everything will be 0. And now if we combine those two terms, n equals 0 to infinity, we can write exponential minus j omega and the power n, and now we have a geometric series. This is a geometric series. But since we have an infinite summation here, we need to worry about its convergence. It might not converge. But we know that for geometric series, the only condition for this series to converge is that this quantity here, or this function here, should be the magnitude or the absolute value. In this case, it's a magnitude because it's a complex. The magnitude of this should be less than 1, strictly less than 1. If it's 1, it will not converge. So strictly less than 1. And this is basically just the absolute value of gamma. And this is satisfied. This is satisfied because we have assumed that this is true from the beginning. So this geometric series will converge. And it will converge to this value. You must be aware of how to find the value of geometric series by now, because we have used a lot. And I think it was provided in the early in this course, maybe in the first week. I'm not sure, but you will find the derivations for this everywhere if you search. So this will converge to this value, 1 minus this thing. So gamma exponential minus j omega. Okay. And this is the exponential j omega. This is the discrete time Fourier transform of a signal of this form, like basically a discrete time exponential signal. And this is exponential because if we try to plot it, if we plot it this way, assuming that gamma is less than 1, the magnitude or the absolute value of gamma is less than 1, so it will decay exponentially. This xn. It will decay exponentially. So we call this a discrete time exponential signal. And its Fourier transform, discrete time Fourier transform is of this form, which is similar to what we got in the I've removed it in the continuous time. It's similar to a little bit similar to what we got in the continuous time Fourier transform of the exponentials of a causal exponential signal. Let me write it here just to remember that this is the Fourier transform of this signal with gamma less than 1.